Hey, this is Math 7, Unit 8, Lesson 6, Estimating Probabilities Using Simulation. So we're going to simulate some real-world situations and talk about how that affects probability. So first of all, we begin with a little four spinners here for you to think about and talk about with your partners or your class, or maybe just make some notes if you're working at home, on which spinner does not belong. Now, all four of these are different spinners, obviously. They have different colors, different numbers of colors, and different size and spacings. So just like we've done throughout the whole year, there's probably a reason for why each one of these doesn't fit with the others that you can take a look at and see and have a discussion about which one doesn't belong. There's not a right or wrong answer as always, but there's one in each kind of situation you can say, well, because of this reason, I don't see that belonging. So for example, this first spinner, why would it not belong? Well, when we look at it, unlike all the other ones, it has 1, 2, 3, 4 equal parts. There are no other ones with 4 equal parts. We have 4 here, but they're not the same. These 4 here are not the same. This has 3, and these are not all equal parts. So this one's the only one that has 4 equal sections or parts in it, unlike the rest. When you look at this one, why might it not belong? Now look at the colors. What do you notice? We have 1, 2, 3 colors. This one only has 3 colors, or it might say 3 outcomes. That's kind of terms we've been using, right? There are only 3 possible outcomes that would be in this one here. So that's going to be a problem, right? Just not going to quite work out. When you look at this one, this is the only one that for the R, look at that size there. Do you see any other spinner that has more than 50% of the space taken up? I don't. So this is the only one that has a section that has a probability that is greater than 0.5. That's the only one that has a section that has a probability greater than 0.5. So maybe that's why that one doesn't belong. And then perhaps finally, why does this one not belong? Well, maybe because it should be more like that one. The green's less than a fourth. I don't know. Just think of a reason for why it doesn't belong. There's no right or wrong. Again, it's just more of a conversation starter for why you think it doesn't belong there. Okay? And again, there might be some that you said, well, a conversation could be, a question could be, which one would you pick? If you had to select a spinner to spin in order to win a prize, which one would you use? You know, I might say I'd use this spinner if I got to choose red, right? If I thought I wanted to be equal and fair for everybody, I might choose this one right here. So just things to think about and talk about. Okay. In the next activity, there are 3 different things you might be doing in class today. Okay? Your teacher's going to give your group some supplies for one of 3 different simulations. So a simulation is just like an activity, we're going to try something out. Instead of like testing it out in the real world, we simulate it. We pretend that it's happening and record the results to see what could be an outcome. Okay? So we're going to follow instructions to simulate 15 days of Diego's walk. So Diego's not actually walking, we're just pretending that he is walking by using a simulation. Okay, so simulate 1 day. So if your group gets a bag of papers, you're going to reach into the bag, select one paper without looking inside. That paper is going to probably say he's walking or he's taking a break or waiting. Okay, depends on what it's going to be. If you have a spinner, you're going to have a spinner you're going to spin. And you see where it stops, and you record the results. If you get 2 number cubes, which is what I'm going to use today, you're going to roll those, add the numbers that land face up, and if it's a sum of 2 to 8, then it means he has to wait. So that means that if it's 1, well, you can't get 1 really, right? You can't roll and get a 1 unless it rolls off the table. So if I get a 9, 10, 11, and 12, then it tells me that he gets to continue his walk. And that's what we're going to use for our simulation here, because it's just simple to do that. We're going to record it in a table, which is on the next page, okay, whether he had to wait more, and we'll keep track of that. And then we're going to add the fractions together in a cumulative way so we can see how long he has to wait so far. And then we'll plot that on the graph, and then we'll connect the points, and then we'll see what we have, okay? So let's take a look here at our simulation. We're going to go from, I'm not going to do the graph yet, we'll come back to that. So you want to turn to your page that has the place to keep track on whether or not Diego has to wait more than a minute. So for us, remember that if he gets a 2 through 8, then he has to wait. So 2 to 8 equals wait. Okay? So the question is, does he have to wait more than 1 minute? So the first one was a 0, it said. It started us off here for what's happening. So let's see what happens when we roll for time number 4. And we're going to keep track. So we rolled a 4. So the 4 means does he have to wait? Yes. So the total days he's waiting so far, that's going to be another day added to it. He's had to wait 3 days. So he's waited 3 days out of 4. Remember to change your denominator each time. I remember last time I did one of these with you guys, I forgot to do that and had to erase the whole thing. So what is 3/4? That's about 0.75. And actually it equals 0.75, so we can say that. Okay, let's do another one. This time you got an 8. 8 means wait. So we're going to wait again. Whoops, broke my pencil there. So 4. So now we're waiting for day 4 out of 5. And 4 out of 5 is 0.80. Roll again. Got a 7. 7 means I'm going to wait. So we're going to wait again. We're waiting 5 times out of 6. So 5 out of 6, not quite sure what that is. So I'll divide 5 divided by 6. And we get about 0.83. Okay, keep on going. Roll it again. Got another 7. That's another yes. So we're going to wait again. This is day 6 of waiting out of 7. So 6 divided by 7 is about 0.85. Okay, roll it again for day 8. Got another 7. So that's going to be another waiting day. So 7 out of 8. What is that going to be? 7 divided by 8 is about, well, it's 0.875. Let's roll it again. Let's shake them up a little more. Maybe we can get a... Diego hasn't waited for a long time. Hey, got another 8. Oh boy, gotta wait again. So that's gonna be 8 out of 9. So 8 divided by 9 is about 0.88. Roll it again. 5, gonna wait again. So it's another day of waiting. That's 9 out of 10, so that's 0.90. Do it again. Another 8. Wow, so we're waiting again. 10 out of 11. So what is that as a fraction or as a decimal? Oops, we do 10 divided by 11. So we're at about 0.9, we can round it up to 0.91. Got a 7 again, so we're waiting again. It's 11 out of 12, which is going to be 0.916. And we do it again. Boy, this is not working out so well, is it? A 7 again. Wow. So there we are, 12 out of 13. Poor Diego. Well, I guess it's good he's never waiting, but I don't know what that means. 0.92, so about 0.92. Try another one. A 6. So is he waiting again? Yes, he is. 13 out of 14. So what's that going to be? 13 divided by 14. 0.92 or 0.93. And finally, day 15, he gets another 7. He's waiting again. So he's had to wait 14 out of 15 days. 14 divided by 15 days. So again, about 0.93. Wow. So now we want to take this information, which is probably a little off from what it should be because we rolled a lot of bad numbers. We never got anything higher than an 8 the entire time, which is unusual. Which tells me again, I probably need to get some new dice. These ones just are not working out too well, are they? But who knows? So let's see what happens. Let's go back and plot this here. We're going to use this chart and we're going to plot the points we had. And this is the fraction of days he had to wait. So on day 4, we were at 0.75. So we'll plot that right here at 0.75. On day 5, we're at 0.80. So we'll plot that there. Day 6, 0.83. So we'll plot that there. Day 7, 0.85. Plot it there. Day 8, 0.875. A little bit more. Day 9, 0.88. Day 10, 0.90. 91. 91.6. 92. 93. 93. 93. Okay, so we have these points plotted on this graph. And they want us to connect the lines, so we'll connect them like this. Alright, there we go. Now that's what we have so far based upon using my exciting dice. So based on the data you've collected, do you think the fraction of days Diego has to wait after the 16th day will be closer to 0.9 or closer to 0.7? Well, based upon my graph, we're going to go with 0.9. It does seem to be closer to that. Okay. Now, is that accurate or not? I don't know, but it does seem to make sense for what we've done so far. Right? Just take a look. When we roll another one, we're going to guess. The question we're asking here is our next point going to be closer to 0.9, which is along this line right here, or along this line right there? Well, based upon what we're seeing, we're going to go with closer to 0.9. That just makes the most sense from our experiment. Again, this is our experiment. It may not be perfect. It's our simulation. All right, so it says let's go ahead and complete it for the next one. Let's keep on going. All right, so we left off at 14 out of 15 is where we left off here, just so we know where we're at there. Okay, and he's waited a total of 14 days so far. Right, 14 days, which seems, yep, 14 days. Yep, only one day you didn't have to wait. So here we go. So day 16. We got a 6. You know what I'm going to do? I'm going to get some different dice. Because this one just doesn't seem to be playing fairly, I would say. So let's try these ones. Alright. Alright, I have some white ones now. Let's see how these ones work. Maybe we get different results. I don't know. Hey, look at that. Another 8. So does he wait again? Yes, he does. So now we're on day 15. 15 out of 16. So 15 divided by 16 is 0.93. 17. We got a 10. Yay! Does it have to wait? No. Hooray. So now we are at 15 out of 17. The first no we've rolled the entire time. Oops. So 15 divided by 17. We're going to finally go down a little bit. What do you know? So 0.88. And this is why you do these things, right? It's kind of fun a little bit. You never know quite what you're going to get. And if I did the whole thing again, who knows? Let's try another one. Another 8. Ah, yes, he has to wait. So we're going to wait, in this case here, 16 out of 18, which we do 16 divided by 18, and we get 0.88 again. So about 0.88 still. Try another time. Another 8. So we're waiting again. 17 out of 19. So 17 divided by 19 is 0.89. About that. There's a 7. We're going to wait again. So that's 18 out of 20. 18 divided by 20 is 0.9. We'll do it again. Hey, look at that. We rolled a 12. No waiting. Way to go. So 18 out of 21. 18 divided by 21, which is going to drop us down quickly. Imagine that. To 0.85. Alright, gonna roll another one. Got a 9. No waiting there. So that's good news. 18 out of 22. So we divide that. 18 divided by 22. And we have 0.81. Try another one. Got a 7. That's going to be a yes on waiting. So 19 out of 23. Just 0.82-ish. Alright, rolled a 7. Another waiting day. So that's 20 waiting out of 24. 20 divided by 24. Whoops. 20 divided by 24, which is a 0.83 again. And we will go one more time. Hey, we got a 10. That's going to be a no. So that will be a 20 out of 25, which is an even 0.80. Oh my goodness. Well, hey, with the different dice, we at least got some no's in there for the first time. That's interesting if you ask me. Now let's plot these points back in our graph, okay? So we're going to plot, starting at 16 is 0.93. So we're still here. 17 is 0.88, so we're going to dropping below the line a little bit, followed by another 0.88, followed by 0.89, so back up a little bit, 0.90, and then 0.85, so we drop down, 0.81, dropping down, 0.82, going back up, 0.83, a little back up, back to 0.80 down there. So our graph then, when we continue this, drops below the 9, creeps back up to the 9, drops back down, goes up, and drops back down. So now we're in the middle of the 9 and 0.9 and 0.7. Okay, so it's interesting there. So what do we notice about the graph? Well, in our case, it does seem to be leveling off a little bit, right? So leveling off a little bit. It seems to be getting lower in our case here because of just what it was. We were going up high, pretty high, and now it's going a little lower than before, so it's dropping there, and it's more at about 0.80 overall. So based on the graph estimate the probability Diego would have to wait more than 1 minute to cross the crosswalk. Well, the probability of that happening, right, for us, we would say is about 0.80. Looking at where we are here, if this was to continue, you might say about 0.80, but based upon our stuff, we might say more like 0.85, because that's probably more like in the middle of all these points. So somewhere in that range is what we would estimate. Is it accurate? Well, that's hard to say exactly. Again, this is a simulation. If you think back to what we had, we're saying our number choices, the outcomes were things like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those were all of our possible outcomes. And he had to wait if these happened, right? If any of those happens. Which meant that he had to wait if it was 1, 2, 3, 4, 5, 6, 7 things out of 8, 9, 10, 11. So 7 out of 11 possibilities were going to be a wait kind of thing. Which meant that our probability, based upon the outcomes given with the die, was 7 divided by 11, which is 0.63. So we would expect to have something around 0.63, but for us, in our simulation, we got a much higher result, didn't we? We got 0.8, another 0.85, and at one point we're up at the 0.9, so it just didn't make a lot of sense. So the reality is we showed something a little lower, but we just didn't. And that could have been because of the die we were using. Maybe, you know, if we had used this set of die the first time, how would that have changed? Would that have changed things? Well, think about this. We did 10 rolls right here, and in these 10 rolls we had 1, 2, 3, 4 no's. We had a 4 out of 10 on the no's, and we actually had 6 out of 10 on the yeses. So a 6 out of 10 is what? 0.60. Well, is that number closer to this number? It sure is. So what do we notice? With this set of die, we got a result that was closer to what our predicted probability was supposed to be, which tells us there's probably something a little funny about these die. Let's try it again. I mean, I'm just curious. If I roll it right now, will I get a number? What do you think? Will we get something between 2 and 8 or higher than 8? If you had to guess, based upon these things, I would say it'll be less than 8. Let's see. Look at that. We got a 9. So when you're planning on it, you don't get it, do you? And that's the joy of chance, right? Because it's still chance. And there's a 5, there's a 3, there's a 3, finally a 12. So we finally got some bigger ones, but it took us quite a while, and it's chance. You just never, ever know. Oh, boy. Okay. Let's move to the next activity. Activity 3. And skip. Are you ready for more? We're going to 6.3, designing experiments. This is just something for you to think about and talk through. So it says, for each situation, describe a chance experiment that would fairly represent it. So 6 people are going out to lunch. One of them will be selected at random to choose which restaurant to go to. Who gets to choose? So what's an experiment you could use to figure out a way that 6 people could be randomly selected to choose where to go for lunch? Okay? I would probably suggest you use some sort of number cube, right? And each person gets a number, right? And so if you roll a 1, then person number 1 gets a pick. That's fair because there are 6 sides to number cube. That's fair there. Number 2, after a robot stands up, it's equally likely to step forward its left foot or its right foot. So which foot will it use for its first step? If you want to predict that and have a way of a chance experiment, you want to get a 1 out of 2 chance or a 50-50 chance, maybe you just need to flip a coin. Why? Because a coin has simply a heads and a tails, much like left and right. That'd be a great way of checking it out. Computer game, there are 3 tunnels, Each time the level loads, the computer randomly selects one of the tunnels to lead to the castle. Which tunnel is it? Well, I can't flip a coin. Coin is 2. I could do a number cube and just say that 1 and 2 are for something. I could say 1 and 2 are for tunnel number 1, 3 and 4 are tunnel number 2, and 5 and 6 are tunnel number 3. That could work. Or I could draw a spinner, and I can make 3 equal parts, and I can have them labeled for tunnels 1, 2, and 3. Those are options too, right? So all different things that you could do for that. And then finally, your school's taking 4 school buses on a field trip. Will you be assigned to the same bus your math teacher's riding on? Well, you could assign a color for each one of the school buses, right? And they could draw one out of a bag, and if you get the right color, then it's the one the math teacher's on. Let's say the math teacher's on red, and you go, oh, did I get the red one? Oh, I got yellow. Nope, I'm out. I can't go. So, anyways, possibilities there. Here's our summary. Sometimes it's easier to estimate a probability by doing a simulation. A simulation is an experiment that approximates a situation in the real world. Okay, so it's useful when it's hard or time-consuming to gather enough information to estimate the probability of some event. So a simulation is just an experiment that you do to see what might happen in the real world. And of course, I'm doing all these videos today while most of the schools in America are closed because of the simulations that people are running based upon viruses and what could happen there. So how are those numbers being generated? They're doing a simulation to say, if this spreads this way, then this happens. So they're actually doing the same math things you're doing right now. Amazing. That's it for right now. We're going to pause there and let you work on your homework, and we'll come back and check it together in just a few minutes. Okay, here's homework for Lesson 6, Unit 8, Math 7, Estimating Probabilities Using Simulation. The weather forecast says there is a 75% chance it'll rain later today. Draw a spinner you could use to simulate this probability. Okay, so we want to draw a spinner. Ooh, nice circle there. That shows 75% chance of rain. So 75% is about 3 out of 4 or 3/4. I always think about like money, right? 75 cents is going to be 3/4 out of $1, right, to make 75 cents. So 3/4, okay, and maybe you draw a little rain cloud here. So if the spinner lands on that, you got rain, and over here it's sunny. And it's a sunny, happy day. Right now, it's raining at my work. That's all okay. But there are no kids here, so I don't have to worry about being in the gym with a bunch of kids and their food. Yay. Okay, B, describe another way you could simulate this probability. So how else could you do that? Well, here's another way. I could take, for example, I could take 3 blue cubes and 1 yellow cube like so, and I could put them in a bag, and we could say, well, if you draw one out, it's going to be rainy for blue, right? So I can make the blue ones equal rain. I can make the yellow one equal sunny, so sunshine. And if you draw one out, then whatever you get, oh, it's going to be rainy. Shuffle them up again. Oh, sunny, right? Same thing. So that's the idea there. Cool. So that's another way. Number 2, an experiment will produce 1 of 10 different outcomes with equal probability for each. So 1 in 10. Why would using a standard number cube to simulate the experiment be a bad choice? Well, a number cube has how many possibilities? 1 in 6. Those do not match. So why is it a bad choice? Well, it's going to be a bad choice. You want to explain this here, so use some words. Excuse me. It's a bad choice because the number of outcomes is different from the number of outcomes you would expect with the experiment, right? We want 1 out of 10, not 1 out of 6. And even if you were to use 2 cubes, you would have a 1 out of 12 chance if you use 2 cubes. So even that doesn't match our 10, so it's also still a bad choice. Number 3, an ice cream shop offers 40 different flavors. To simulate the most commonly chosen flavor, you could write the name of each flavor on a piece of paper and put it in a bag. You draw from the bag 100 times to see which flavor is chosen the most. Why is that a bad way to figure out the commonly chosen flavor? Well, let's think about this. There are 40 flavors. If you put the name of each one in a bag, that means there is a 1 in 40 chance of drawing that flavor from a bag if you do it 100 times. Even if you do it 100 times, each flavor only has a 1 in 40 chance. Well, that's good in terms of just saying if you were to assign someone a flavor, if they walked in and said, you get to get chocolate, you get strawberry, whatever it might be, if you want to assign it. But because people get to choose, and they're choosing their favorite, right? Most people don't have the same favorite. So what's chosen, though, is not random, okay? A commonly chosen flavor is not a random thing. That's based upon preference or taste. Okay, so the actual situation is going to be different. So this is good for just randomly assigning something, but when people get to choose because you're choosing your favorite, well, that's going to be something different. It doesn't quite work out. All right, number 4, a little review here. Each set of 3 numbers represents lengths and units of the sides of a triangle. Which set cannot be used to make a triangle? And the key thing with a triangle is that the sides A and a side B need to at least equal C, or they need to be greater than C if I'm going to make this work. Okay, when I add that up. If it's less than, then it won't reach. And we tried this before with some different things. Like if I make a line of 2 and a line over here like this, and I have a short line, it's just, oh, hiccups, goodness gracious, not going to work out too well. So in this case here, we have 7 and 6, which add together to make 13, which is less than this number here. So it tells us that this one probably is not going to work. In this case here, 4 and 4 add up to 8. That's greater than 4. And in this case here, 6 and 6 can add up to 12, which is greater than 2. And you might think, what about over here? Well, I could do 6 and 2, which adds up to 8. That's also greater than the number 6. So different ways of looking at it, it still works. So A is the one that would not become a triangle. Oops, there's one more on the back page. We have 7, we have 8, and we have 13. I didn't see that one there. And when you add those up, you end up with 15, which is still greater than the last or the third side. All right, let's look at number 5. I hope my hiccups go away. There is a proportional relationship between a volume measured in cups and the same volume measured in tablespoons. If we have 48 tablespoons, it's equivalent to 3 cups. So we could write tablespoons, we could write cups, and make for ourselves a nice little chart here. So we know 48 tablespoons is equivalent to 3 cups, like so. All right, plot and label some more points. Well, let's drop our cups down to 1 by dividing by 3. When I do 48 divided by 3, I end up with 16. Okay, so there's another point there. We can come out to 16. So we go on our chart down here, 10, 12, 14, 16, and 1. That's another point. We can make one for 2 now by multiplying by 2. Multiply by 2, that becomes 32. So at 32, we're at 2 cups. We're good there. And if we want to make one for 4, since we're here as well, we do 2 times 2, which is 4, and 32 times 2 is 64. So we can count 64 and plot a point right there. So now we have 4 different points there. We can plot them, label them, use a straight edge to draw a line that represents this proportional relationship. So we can come out to this point here, line that there, and draw my line to show the proportional relationship. Okay. So for which value y is 1 comma y on the line you just drew? Well, 1 is over here, isn't it, right? So we're wanting to know, well, it's right here actually, technically, right here in the middle. So what is the value of y right there? That's really hard to tell, isn't it? But I could look on my chart and figure this out. Let's say I use my 16 comma 1 again, this one here, and I want to reduce this down to 1 because that's the x value, is the 1. So that means dividing by 16. So when I do 1 divided by 16, what do I get? I get 1/16. So the value for y that is right there would actually be 1 comma 1/16. Okay, so we have 1/16. Our constant proportionality becomes the value that I multiply this side by to get that one. So what number times 1 gets you to 1/16? It's 1/16. Okay? If you think of it this way, look at this one here. If I did 16 times 1/16, that's my constant proportionality, what do I get? I get 1, which is exactly what we see right there. So for our equation, the equation was always y equals the constant proportionality times the x value. This is my x, this is my y. So my y is cups, so we're going to say cups equals the constant proportionality, which is the 1/16, times the x value, which in this case is t for tablespoons. So there's my equation. This is a great review back from Unit 2, something you want to keep in mind all the time. That's it for today. Have a great day, and we will see you next time.